What if I told you that right now, in laboratories scattered across the world, machines are beginning to think in ways that mirror the very fabric of reality itself? What if the key to unlocking the deepest secrets of the universe wasn't buried in the heart of a distant galaxy, but instead humming quietly inside a quantum processor no larger than your fingernail? This is not science fiction. This is happening right now. In the last few months, something extraordinary has begun to unfold at the intersection of two of humanity's greatest scientific achievements. Quantum computing, a technology once dismissed as decades away from practical use, has suddenly leaped forward with capabilities that have left even seasoned physicists stunned. And at the same time, researchers working with data from the Large Hadron Collider have discovered anomalies in the behavior of the Higgs boson, the so-called God particle, that seem almost impossible to explain using our current understanding of physics. But here's where it gets truly remarkable. Some of the world's leading experts in both fields are now suggesting that these two breakthroughs might be connected in ways we never anticipated. That quantum computers, with their ability to process information using the same strange rules that govern subatomic particles, might be giving us our first glimpse into a hidden layer of reality. A layer where the Higgs field, the invisible force that gives everything in the universe its mass, operates in ways far more complex and profound than we ever imagined. Welcome to a journey that will take us from the frozen corridors of CERN in Switzerland to the cutting-edge quantum laboratories of IBM and Google. We're going to explore one of the most exciting and controversial ideas in modern physics. And by the end, you'll understand why some scientists believe we may be standing at the threshold of a revolution that will change everything we know about existence itself. But before we dive into what's happening right now, we need to understand the two incredible pieces of this puzzle. And that means going back to a question that has haunted physicists for over a century. Why does anything have mass at all? Think about it for a moment. You're sitting there, watching this video, and you have weight. You can feel gravity pulling you toward the earth. The device you're watching on has weight. The chair beneath you, the air in your lungs, every atom in your body, everything around you has mass. But why? What actually gives matter its heft, its substance, its resistance to being pushed around? For most of human history, this seemed like a question that didn't need asking. Things had mass because, well, they were things. It seemed obvious. But when physicists began probing the subatomic world in the 20th century, they discovered something deeply troubling. According to their equations, according to the mathematics that described how particles interact with each other, nothing should have mass at all. The fundamental particles that make up atoms, electrons, quarks, all of them should be completely massless, zipping around at the speed of light like photons of light themselves. Obviously, that's not what happens. We're not all moving at light speed. We have weight, we have substance. Something was missing from the equations. Something huge. In 1964, a theoretical physicist named Peter Higgs, along with several other scientists working independently, proposed an elegant solution. They suggested that the entire universe is filled with an invisible field, a kind of cosmic molasses that permeates every corner of space and time. When particles move through this field, they interact with it, and that interaction is what gives them mass. The more strongly a particle interacts with this field, the more massive it becomes. Particles that don't interact with it at all, like photons, remain massless and travel at light speed. This invisible field became known as the Higgs field, and the theory predicted that if you pumped enough energy into a tiny region of space, you could create a ripple in this field, a temporary particle that would briefly pop into existence before decaying away. This ripple became known as the Higgs boson. But here's the thing. For nearly 50 years, the Higgs boson remained theoretical. Scientists believed it existed, but no one had ever seen one. No experiment had ever produced enough energy to create this elusive particle. It became the holy grail of particle physics, the missing piece that would confirm our entire understanding of how the universe works at its most fundamental level. And then, on July 4th, 2012, everything changed. Deep beneath the border between France and Switzerland, inside a circular tunnel 27 kilometers in circumference, the Large Hadron Collider had been smashing protons together at nearly the speed of light for years. On that summer day, scientists from two independent detector teams ATLAS and CMS, made simultaneous announcements that sent shockwaves through the scientific world. They had found it. After decades of searching, after billions of dollars and the collaboration of thousands of scientists from over 100 countries, humanity had finally detected the Higgs boson. The discovery was monumental. Peter Higgs was in the audience that day, tears streaming down his face, as his life's work was finally confirmed. He would go on to win the Nobel Prize the following year. Media outlets around the world celebrated the finding, often using the nickname that Higgs himself had always disliked, the God particle. That name, by the way, wasn't chosen because physicists thought the Higgs boson had anything to do with religion or divinity. It actually came from a book written in 1993 by physicist Leon Lederman. He originally wanted to call it the goddamn particle because it was so frustratingly difficult to find, but his publisher insisted on shortening it. The name stuck, much to the annoyance of many scientists who felt it gave people the wrong impression. The year is 2024, and inside a nondescript building at IBM's research facility in New York, a machine unlike any other hums quietly in a chamber cooled to temperatures colder than outer space. This is one of the most advanced quantum computers ever built, a device capable of manipulating over 1,000 qubits simultaneously, pushing the boundaries of what we once thought computationally possible. But the truly remarkable work isn't happening in the hardware itself. It's happening in the minds of physicists who have begun using these quantum systems to simulate something that has never been simulated before with such precision. The behavior of the Higgs field at energy scales that even the Large Hadron Collider cannot directly probe. To understand why this matters, we need to appreciate a fundamental limitation of particle physics experiments. When scientists at CERN smash protons together, they're creating conditions that briefly existed just fractions of a second after the Big Bang. Enormous energies, extreme temperatures, particles popping in and out of existence in billionths of a second. But even the Large Hadron Collider, the most powerful particle accelerator ever constructed, can only reach certain energy levels. Beyond that, the technology simply doesn't exist yet. This means there are entire regions of physics that we cannot directly explore through experiments. We can only theorize about what might happen at higher energies, in more extreme conditions, in the first instance of cosmic creation. For decades, these regions remained shrouded in mathematical speculation. But quantum computers are changing that equation. Because quantum computers operate using the same fundamental principles that govern subatomic particles, they can simulate quantum systems with a fidelity that classical computers cannot match. Instead of approximating quantum behavior using classical mathematics, which always involves compromises and shortcuts, quantum computers can model quantum reality directly. It's like the difference between reading a description of the ocean and actually swimming in it. And when researchers began using these machines to simulate the Higgs field at extreme energies, they discovered something that no one had anticipated. The Higgs field, according to our standard understanding, should be relatively simple at its core. Yes, it permeates all of space. Yes, it gives particles their mass through a well-understood mechanism. But fundamentally, it was thought to be a single field with a single associated particle, the Higgs boson, behaving in predictable ways according to well-established equations. What the quantum simulations revealed was something far more intricate. At energy scales beyond what the Large Hadron Collider can currently achieve, the Higgs field appears to exhibit behaviors that suggest hidden layers of complexity. Interactions that shouldn't exist according to the standard model. Resonances that hint at additional particles or fields that we haven't yet detected. A mathematical structure that seems almost modular, as if the Higgs mechanism we've observed is just one component of a much larger system. This is where the plug-in metaphor comes from, and why it has captured the imagination of physicists and the public alike. Think about it like this: when you use software on your computer, you might install plugins that add new functionality. The core program works on its own, but the plugin enhances it, gives it new capabilities, connects it to other systems. Some experts are now suggesting that what we've been studying as the Higgs boson might be analogous to just one plugin in a much larger cosmic operating system. A single module that we've successfully identified and measured, but which connects to other modules that remain hidden from our current experiments. Dr. Maria Spyropoulou, a particle physicist at Caltech who has spent her career studying physics beyond the Standard Model, was among the first to publicly discuss these findings. In a presentation at a quantum computing conference earlier this year, she described the emerging picture as humbling and exhilarating in equal measure. The simulations, she explained, suggest that the Higgs sector of particle physics might be far richer than our current theories describe. What we've discovered might be just the tip of an iceberg that extends into physics we don't yet understand. But here's where the warning comes in and why it has generated so much discussion in the scientific community. When you're dealing with simulations, especially simulations of systems that cannot be directly verified through experiments, you're always walking a fine line between discovery and speculation. Quantum computers are extraordinarily powerful, but they're also extraordinarily sensitive to errors. A single qubit flipping unexpectedly, a tiny amount of interference from the environment, and your entire simulation can produce results that look meaningful but are actually artifacts of the computation itself. Some physicists have urged caution in interpreting these findings. Dr. John Preskill of Caltech, one of the pioneers of quantum information science, has emphasized that while the simulations are intriguing, they need to be validated through multiple independent approaches before we can draw firm conclusions. We're in new territory, he noted in a recent interview. Quantum computers give us unprecedented power to explore theoretical physics, but that power comes with the responsibility to be extremely rigorous in how we interpret results. This tension between excitement and caution is at the heart of the current scientific conversation. On one side, researchers see the quantum simulations as potential windows into physics beyond the Standard Model, offering clues that could guide the next generation of experiments. On the other side, skeptics worry that we might be reading patterns into noise, seeing structure where there is only computational error. But regardless of where you fall on that spectrum, one thing is becoming increasingly clear. The combination of quantum computing and particle physics is opening doors that were previously sealed. We are developing tools that allow us to ask questions about the universe that couldn't even be formulated a generation ago. And some of those questions strike at the very foundations of reality. Consider for a moment what it would mean if the Higgs field really does have hidden complexity. If the mechanism that gives particles their mass is just one part of a larger system that we haven't yet uncovered. It would suggest that the universe is even more deeply structured than we currently appreciate. That there are layers of reality beneath what we can see, principles of organization that shape everything from the smallest particle to the largest galaxy. This idea resonates with one of the most exciting frontiers in theoretical physics: the search for a unified theory that could bring together all the fundamental forces of nature. For over a century, physicists have dreamed of finding a single framework that would explain gravity, electromagnetism, the strong nuclear force, and the weak nuclear force as different aspects of a single underlying principle. The Standard Model, for all its success, is incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It has gaps that cry out to be filled. Could the hidden structure of the Higgs field be a clue to that unification? Could the plugins that quantum simulations seem to be revealing be connected to the forces and particles that a unified theory would predict? These are not idle speculations. They are active areas of research being pursued by some of the brightest minds in physics. And the tools that quantum computing provides are accelerating that research in ways that would have been unimaginable just a few years ago. At the same time, the practical implications of this work extend far beyond pure science. Understanding the deep structure of matter and energy has always led to technological revolutions. The discovery of the electron led to electronics. The understanding of nuclear forces led to nuclear energy. The development of quantum mechanics led to semiconductors, lasers, and eventually the computers and smartphones that define modern life. If we truly are uncovering new layers of the Higgs field, new aspects of how mass and energy interact at fundamental levels, it's impossible to predict what technologies might eventually emerge. We might develop new ways to manipulate matter, new sources of energy, new methods of computation that make even today's quantum computers look primitive. The history of physics teaches us that the most profound discoveries often have the most transformative applications, even if those applications take decades or centuries to fully realize. But for now, we are still in the early stages of this journey. The quantum simulations that have revealed these hints of hidden structure are just the beginning. The Large Hadron Collider is undergoing upgrades that will allow it to collect far more data and probe higher energies. Next-generation quantum computers with more qubits and lower error rates are being developed at laboratories around the world. Theoretical physicists are constructing new mathematical frameworks to interpret what we're learning. And throughout all of this, one thing remains constant: the profound human drive to understand. To look at the universe in all its mystery and complexity and ask, how does this work? Why are we here? What lies beneath what we can see? That drive has carried us from ancient astronomers gazing at the stars to modern physicists manipulating the quantum fabric of reality. It's the same curiosity, the same wonder, the same refusal to accept that some questions are too big to answer. And in that spirit, let's turn now to what all of this might mean for the future. Not just the future of physics, but the future of humanity itself. Because if we truly are on the verge of understanding reality at a deeper level than ever before, the implications extend far beyond academic journals and research laboratories. They touch on who we are, where we're going, and what kind of universe we actually inhabit. There is a photograph that hangs in many physics departments around the world. It shows a group of scientists at the 1927 Solvay Conference in Brussels, a gathering that brought together some of the greatest minds in the history of science. Albert Einstein is there, arms crossed, looking slightly skeptical. Marie Curie sits in the front row, the only woman among the attendees, her expression calm and confident. Niels Bohr, Werner Heisenberg, Max Planck, Erwin Schrödinger, Paul Dirac, the names read like a who's who of 20th century physics. These were the people who revolutionized our understanding of reality. In just a few decades, they overturned centuries of classical physics and revealed a quantum world so strange, so counterintuitive, that even Einstein himself never fully accepted it. They discovered that particles can be in two places at once, that observation affects reality, that the universe at its smallest scales operates according to rules that seem to defy common sense. And yet, as revolutionary as their discoveries were, they knew they were only scratching the surface. Einstein spent the last decades of his life searching for a unified field theory, convinced that there must be deeper principles beneath what they had uncovered. He never found it. The quest continued after his death, and it continues to this day. What makes our current moment so extraordinary is that we may finally have the tools to complete that quest. Not because we're smarter than Einstein or Bohr or Curie, but because we have something they didn't: machines that can think in quantum. Quantum computers don't just calculate faster. They calculate differently. They can hold multiple possibilities in superposition, exploring vast landscapes of potential solutions simultaneously. They can model quantum systems with a precision that classical computers could never achieve. And when we point these machines at the deepest questions in physics, the nature of the Higgs field, the structure of space-time, the origins of mass and energy, they show us things we couldn't see before. This is what makes the recent discoveries about the Higgs field so significant. It's not just that we've found new anomalies in the data. It's that we finally have the computational power to make sense of what those anomalies might mean, to build simulations and models that can test theories against the strange behavior we're observing, to follow the clues wherever they lead, even into territory that our classical mathematics couldn't navigate. And where might those clues lead? One possibility that has captured the imagination of many physicists is the existence of what's called an extended Higgs sector. In the Standard Model, there is just one Higgs field and one Higgs boson. But many theories beyond the Standard Model predict additional Higgs particles, a whole family of related bosons with different masses and properties. Some versions of supersymmetry, a theoretical framework that proposes a partner particle for every known particle, predict as many as 5 different Higgs bosons. If the quantum simulations are correct, and the Higgs field really does have hidden complexity, it could be evidence that these additional particles exist. They might be too heavy for the Large Hadron Collider to produce directly, but their effects could ripple down into the behavior of the Higgs boson we can observe. The plug-in other words, might be showing us shadows of a larger system that remains just beyond our reach. Another possibility is even more profound. Some physicists have suggested that the unusual behavior of the Higgs field might be connected to the nature of space-time itself. In certain theories of quantum gravity, the Higgs field doesn't just give particles mass, it's intimately connected to the structure of space and time at the smallest scales. Changes in the Higgs field could correspond to changes in the fabric of reality itself. If this connection turns out to be real, it would be one of the most important discoveries in the history of science. It would link the world of particle physics to the world of gravity and cosmology. It would offer a pathway toward the unified theory that Einstein sought. It would reveal that the same mechanism that gives an electron its mass also shapes the curvature of spacetime around a black hole. We are not there yet. These ideas remain theoretical, speculative, works in progress. But the fact that we can even explore them, that we have tools capable of probing these questions, is itself remarkable. A century ago, the scientists at Solvay could only dream of such capabilities. Today, we are beginning to make those dreams real. And this brings us to perhaps the most important lesson of all. Throughout human history, our greatest advances have come not from finding final answers, but from asking better questions. Every discovery opens new mysteries. Every answer reveals new puzzles. The universe, it seems, is infinitely deep. The Higgs boson was supposed to be the last piece of the Standard Model puzzle. Its discovery was celebrated as a triumphant conclusion to a decades-long search. But instead of closing a chapter, it has opened a new one. Instead of answering all our questions about mass and matter, it has revealed how much we still don't know. The God particle, it turns out, is not an ending. It's a beginning. And perhaps that's exactly as it should be. Perhaps the universe is designed, if we can use that word, to always stay one step ahead of our understanding. Every time we think we've figured it out, reality reveals another layer, another mystery, another invitation to keep exploring. There's something deeply moving about that idea. It means the adventure never ends. It means future generations will have their own discoveries to make, their own revolutions to spark, their own moments of wonder and revelation. The quantum computers we build today will seem primitive to scientists a century from now, just as the equipment used at Solvay seems primitive to us. But the spirit of inquiry, the passion for understanding, the sheer awe at the magnificence of existence, that never ages. When we peer into the quantum realm, when we study the Higgs field and the mysterious forces that shape our universe, we are doing more than just science. We are participating in a tradition that stretches back to the first humans who looked up at the stars and wondered what they were. We are connected to every philosopher, every astronomer, every physicist who ever asked, why, how, what does it all mean? And maybe that's the real message of these discoveries. Not just that the universe is strange and beautiful and full of surprises, though it certainly is all those things, but that we, these tiny beings on a small planet orbiting an ordinary star in an unremarkable corner of one galaxy among billions, have the capacity to understand it. That our minds, made of atoms forged in ancient stars, can somehow grasp the principles that govern those same atoms. That we are the universe becoming aware of itself. What could be more miraculous than that? So where do we go from here? The Large Hadron Collider will continue its work, smashing particles and collecting data, searching for signs of physics beyond the Standard Model. Quantum computers will grow more powerful, enabling simulations of ever greater complexity and precision. Theorists will develop new frameworks, new equations, new ways of understanding what the data reveals. And somewhere, perhaps in a laboratory that hasn't been built yet, or in the mind of a student who is just beginning to ask questions, the next breakthrough is waiting. That breakthrough might come from the Higgs field. It might come from dark matter or dark energy. It might come from gravitational waves or black holes or the cosmic microwave background. Or it might come from somewhere completely unexpected, from a direction no one is currently looking. That's the beauty of science. You never know where the next revelation will emerge. You only know that if you keep asking questions, if you keep building better tools, if you keep pushing the boundaries of what's known, eventually the universe will give up another one of its secrets. And what a privilege it is to be alive at a time when those secrets are being revealed. What an extraordinary moment in history. Our grandparents could barely imagine computers. Our parents watched humans walk on the moon. And we are witnessing the birth of quantum computing and the exploration of the Higgs field at energies never before achieved. We are watching humanity take its first steps toward understanding the deepest structure of reality. There will be setbacks, of course. There always are. Some theories will turn out to be wrong. Some experiments will fail. Some discoveries will raise more questions than they answer. That's the nature of the enterprise. But the overall trajectory is clear. We are learning more about the universe every day. We are building tools of unprecedented power. We are asking questions that would have been unimaginable to previous generations. And in that asking, we are affirming something essential about what it means to be human. We are curious creatures. We are explorers. We are meaning makers. We look at the cosmos not just with eyes, but with wonder. We don't just accept the world as it is. We ask why it is that way, and whether it could be different, and what secrets remain to be uncovered.